Hi, everybody. This is Mr. Folly, and welcome to part two. Yeah, 101 to who knows where. Where we left, I guess 100 maybe is what we did there. Let's see where we are. Use choices above to identify the type of bonding. So we're doing it from pictures. So let's look at this guy. We're looking at this one right here. So do you see how this is a molecule? This is another molecule. This is another molecule of water. And our choices are ionic, covalent, metallic. So this is covalent because I have molecules. Notice here it's even labeled delocalized electrons. So see how the electrons can move around and they can go wherever they want. Delocalized means they're not held to one spot. That's metallic bonding, so ionic, metallic, covalent. So metallic is B. Oh, look, big charges. Big charges. That's ionic. So this is big positive, little negative. This has big charges. Look at this, big charges. Ionic. Big positive. Uh-oh. Move that too quick. Big positive, little bitty negatives. That's metallic. Ionic, metallic, covalent. Oops. I'll put M here. Oh. I'll take my deep breath. Hopefully my writing will stick. Hey, it did. This right here, big positive, little negatives. That's metallic, which was B. All right. 107. Popular question in class today. How many valence electrons, single electrons, and bonds does nitrogen have? What you need to know is single electrons equals, let's try this, number of single electrons equals number of bonds. Right? So nitrogen is in column 15, so it looks like this when I draw this little dot. So it has 5 valence electrons, 3 single, 3 bonds. That's it. How many valence electrons, single electrons, and bonds does chlorine have? So chlorine is in the 17th column, has 7 valence electrons, 1 single, 1 bond. How many valence electrons and bonds does potassium have? Potassium's number 19. And potassium looks like this. So it's got 1 valence electron, 1 single electron, and 1 bond. What element is this? Uh-oh, I need my periodic table. So I'm going to get out my periodic table, and all I'm going to look at is the last part. So this says third row. This says P block, and this is the third column in the P block. Third row, 1, 2, 3, P block. Okay, aluminum to argon, and then P3 would be phosphorus. Phosphorus, yeah. Last part. Second row, P block, 4. First row, second row, P block, P1, P2, P3, P4. That's my old friend oxygen. Ooh, 3D. Now remember, 3D is off a row. So 3D is in the 4th row. So row 1, row 2, row 3, row 4. And I'm looking for D6. So D1, D2, D3, D4. So D1 scandium, D2 titanium, D3 vanadium, D4 chromium, D5 manganese, D6 iron. We have iron. All right, and then charges from the periodic table. We should know these. We use these a ton. +1, +2. These are the variable ones. Uh-oh. +3, 0, -3, -2. I got to rewrite it. I knew I didn't make it big enough for myself. +3, 0, -3, -2, 0. And that's how we tell. So bromine is right here, -1. Sodium is right here, +1. Barium is right here, +2. And now we get a look at the next part. What is the charge formed from the ions? Phosphorus, it's in the -3 column. Isotope A is 45%, isotope B is 55%, that's more. The average is closest to the bigger percentage. Newman has found 2 isotopes. Isotope 1 is 90. Isotope 2 has 10. 90 is bigger than 10. How can you tell which isotope is most abundant? It has the biggest. I can tell which isotope is most abundant. The most abundant isotope is closest to the average mass. Closest to the average mass. What is the most abundant isotope of tellurium? Why did I pick such a weird one? I didn't know where it was. There's technetium, tellurium. Looking for tellurium. There's thallium. Looking for tellurium. Oh, this is embarrassing. I thought I knew where all my elements were. Technetium. Tantalum. I know it's TC. I'm about to show you guys a little trick I rarely have to use. I see tellurium. Oh, tellurium, is that what I'm looking for? Yeah, tellurium is number 52. And its average is 127.6. So that means 128 is the most abundant element. Stronger intermolecular forces make boiling points for covalent compounds increase. So increased force increases BP. Whoops, that's not batting practice. Stronger intermolecular forces make surface tension for covalent. Again, increased force increases BP. Remember, intermolecular forces are clumpiness. So if you are clumpy, you're going to be a liquid, which means it takes more energy to make you boil. Whoops, if you're clumpy, you're going to have a much higher surface tension. Stronger intermolecular forces increase forces, makes the viscosity, and that is resistance to flow, and that increases too. My dog is mad at me for not playing with her. Stronger intermolecular forces make evaporation rates. Remember, if you clump more, your evaporation rate goes down. My dog's having fun. Can you hear? Stronger forces, makes vapor pressure. So remember, increased forces means there's less evaporation. So that means there's less pressure from evaporation. So that means increased forces decreases vapor pressure. I guess I should actually circle my answers, huh? All right. Now, stronger intermolecular forces make solubility in water for covalent compounds increase because remember, polar dissolves in polar. I did add the thing in water, which is true. All right, so next time we will take a look at electronegativity. So to that, I will say toodles.